All right, so we're going to go ahead and look at the chapter 11 first section, 11.1. But first, I had a few questions from 10.8 that some folks wanted me to look at, so we're going to start there. So going to take a quick look at a few questions from 10.8. First, some requests for 47 and 49. So 47 and 49 want you to identify the imaginary and complex parts, the imaginary and real parts of these complex numbers. So 47, the first one, is negative 6i. That's entirely imaginary, right? There's no real part to it. So if we were to write it as a full complex term, it would be 0 minus 6i. The real part is 0. So technically, there is no real part. 0 is nothing. So there's no real part. So you could simply say no real part. Or you could write it like this, which also says no real part. We just represent that with a number, in this case 0. And then this is our imaginary part. And same thing for number 49. 35. That's entirely real. There's no imaginary part, right? So you could simply just say there's no imaginary part. So this turns out 35 is not a complex number. 35 is just a number. But if you wanted to write it as a complex number, it would be 35 plus 0i, because there is no imaginary part to this number. It's entirely real. So that's it wasn't intentionally a trick question. It's just literally 0, right? 0 means nothing. So in the case of 47, the real part is 0. In the case of 49, the imaginary part is 0. So that's what that was looking for there. So hopefully that clears up any confusion. The last one that people wanted to go over was 71, and that's definitely a tricky one, a bit annoying to say the least. So let's take a look at that. So we have 2 plus I times 3 minus 2i times 4 plus 3i. So first, let's just look at these first two terms. 2 plus I and 3 minus 2i. One step at a time, right? This is already difficult enough. So just like always, we FOIL that. So that's where we start. We start with a FOIL. So first, outer, inner, and last. So our first is 2 times 3, which is 6. Our outer is 2 times a negative 2i for a negative 4i. Our inner is 3i, so positive 3i there. And then the last is I times a negative 2i for a negative 2i squared, right? Because there's an I in both terms, so an I times an I is an I squared. So now let's simplify. 6 is just 6. A negative 4i and a positive 3i leaves us with a negative 1i, or just negative I. And we have negative 2 times negative 1. Remember, I squared is negative 1, because I is the square root of negative 1. So when we square that, the square root goes away, and we're left with negative 1. So I squared there is negative 1. And this becomes 6 minus I plus 2, or 8 minus I. But we're careful, we're not done yet, right? That was just these first two sections. So we still have to take that and multiply it by the remaining. So we still have to take that 8 minus I that we just got and multiply that by 4 plus 3i. Because the 8 minus I was just looking at the first two groups. We still have that third complex number to multiply in there. So Again, we FOIL. First, outer, inner, last. So 8 times 4 is 32. Outer is 8 times 3i is 24i. Inner is negative I times 4, so negative 4i. And then last is negative I times positive 3i, for a negative 3i squared. And again, same thing as before. So we have 32 plus 20i, right, because 24 minus 4, minus 3 times a negative 1, and that gives us 32 plus 20i plus 3, or 35 plus 20i. So there's our final answer. So just take it one step at a time, right? Start with your first two groups there and FOIL those together. Then you can FOIL with the last group there. So it was a double FOIL scenario there. And again, we have to remember our I power rules. So I squared is negative 1. That was important to remember as well. So hopefully that's making sense to you. If not, just let me know. That's the great thing about asynchronous days is I'm available to help as long as I'm not helping someone else, or in today's case, as long as I'm not watching a biology presentation. So if you still need any assistance on this I concept, imaginary and complex numbers, if it's not clicking for you, let me know, and we can try to work together on it. But hopefully this helps clear up any confusion there. So, with that being said, let's move on. It's a very awkward dichotomy here, moving on to an entirely new chapter. I know that's what happens when we start to run out of time, unfortunately. But moving into chapter 11. Now, chapter 11 actually kind of goes well with chapter 10 because there's still a lot of square roots and squaring involved. Hopefully not a lot of swearing involved, but there's a lot of exponents and square roots and even some complex numbers here or there if we're able to get far enough in this last little bit of time we have here this school year. So yes, chapter 11 is all about introduction to something called quadratics. So that's what chapter 11 is all about. Quadratics. Quadratics, with a Q, is any sort of polynomial that has the highest term is squared. So x squared is an example of a quadratic. X squared plus 3x. You could have x squared minus 4x. Wow, I can't. Great. Plus 7, whatever. In all of those polynomials, remember polynomial just means a number with multiple parts, such as, these. We've got a 3-part polynomial here we call a trinomial on the bottom. But this middle one is a binomial, right? 2 different parts. Another binomial could just simply be x squared, minus 7, right? It doesn't necessarily need to have an x part. That would also be a quadratic, the x squared minus 7. X minus 7 is also a binomial. However, it's not a quadratic because in order to be quadratic, the highest power of the polynomial is a 2. And that leads to a variety of different scenarios. You're probably familiar with the term parabola. What a parabola is, if we look at a graph here, it's this shape. Well, this would be like x squared plus 1 because I missed the axis there. I was going for just regular x squared, but it's floating a little bit above there. So we're going to call that x squared plus 1. But when you have, x squared graph, it's got that parabola shape where it's kind of like the U, or in the case of, wow, I'm not going to settle for graph that terribly drawn. In the case of negative x squared, there we go. That's a pretty good parabola. Negative x squared, it's going upside down, right? Because it's negative now. So quadratics are any sort of term that would give you that parabola shape, where your what we call the leading polynomial, the highest order polynomial, is a squared. So any of these are examples of quadratics, because they are polynomials where our highest power is a square. So that's kind of the introduction to the terminology there. So you can see where a square root might be involved. If we've got a square involved and we need to solve for x at some point, we're going to need to square root, right? So that can take a number of forms. Some other ways you might see quadratics is something like this, where some sort of group, I'm really liking 3 and 7 today apparently, some sort of group is squared. Wow, I need to stop picking 3. That's it. No more 3s. We're going to go with a different number here. There we go. So you might have some sort of group squared. So x itself might not be directly squared, but it's part of some sort of group that is squared. So the x is still squared. It's still an x squared quadratic, even though the 2 isn't directly attached to the x itself, right? Or it doesn't need to be x. It can be any variable, right? We see a used a lot, so let's go like 3a squared plus 9a minus 42 equals 0. That's a quadratic, right? Because a is our variable in this case, and the highest power on that is 2. So we've got ourselves a quadratic here. In this case, quadratic of a being the variable rather than x. So x is just a placeholder. We can use anything we want for x. X is just the most common one. I don't know, sometimes when I'm teaching physics, I find that if I replace some variables with x, it helps students with the math. So I always like to point that out, that x is replaceable. There's nothing really special about x. We can use a, you can use a smiley face emoji, whatever you want. Variables are interchangeable. So anyway, that was a little tangential. Why don't we look at a few example problems here with a few of the techniques for solving these, what we call quadratic equations. And you may have even been exposed to it at some point in your math career, depending on what your Algebra 1 experience will look like. You may have even been exposed to what we call the quadratic equation, which we will certainly get to here shortly within the next few sections here in Chapter 11. But quadratics are all about these squared terms, these polynomials with the squared as the leading power. All right, so first one from the homework is number 3. Let's check that out and see what we got going on here with number 3. Y squared equals 4. Very straightforward. They call this the square root property. And what they mean by that is what we've been saying all year. To undo a square root, to undo a square, you do a square root. It's kind of smashed in there, so I'm going to erase it a little bit. But you saw that. To undo a square, you take the square root of something. So the square root of y squared is just y. Square root of 4 is 2. Here's where that square root property comes in there. And it's something I've been trying to drill into you guys all semester. And it's showing up again. A square root has a positive and negative option. Either one is equally valid. Sometimes, like with physics, there's extra information that lets you know whether it's the positive one or the negative one. But if we don't have any extra information, like in this case, we're not given any information, it's just, here's an equation, solve it. In that case, we don't know if it's positive or negative. So we have to give credit, in a sense, to both answers. So plus or minus 2. So that's all the square root property saying. It's nothing new, really. It's just a reminder of something I've already been explaining all year, that a square root has a positive and a negative option. So now let's look at when this gets a little more complicated. Number 9 here. This is when we have one of those groups squared. So q in this case, instead of x, q plus 3 is squared, and that equals 4. Well, we need to get q by itself. So you might be tempted here to subtract 3, right? We've got a plus 3. We need to get rid of it. We want a minus 3. However, we can't subtract 3 yet because it's part of this group with q. So I've been saying to you guys all year, when you have a group, like in a parentheses in this case, or earlier when we had absolute value or things like that, you can't break up the group. You have to kind of undo the group. So in this case, what does that mean? Well, our group is squared, right? This entire group here, q plus 3, is squared. So to undo that, we need a square root, right? A square root undoes a square. So we've got the square root of q plus 3 squared over here. And over here, we've got the square root of 4. So this just becomes q plus 3, right? The square root undid the square, and notice our parentheses are gone now because there's no more squared. There's nothing happening to this group q plus 3. There's nothing holding them together, right? When they were squared, that square was kind of tying this whole group together and not letting us split it up. Once we got rid of that square with the square root, now we're just left with regular q plus 3, and there's nothing special about that. So now we can subtract 3, but first, before we do that, we need to remember our plus or minus, that this 2 could be positive or negative. We don't know. We have no way of knowing, so we have to list both options there, positive or negative 2. So now when we subtract our 3, we get a negative 3 over here that we either add or subtract 2 from, right? We don't know if that 2 is positive or negative, so it can be both options. So in this case, q could either be negative 1, right? If the 2 is positive, then we've got negative 3 plus 2 is negative 1, or it could be negative 5, right? Because negative 3 minus 2, if that 2 was negative, gives us a negative 5. So again, that's probably the two most common mistakes of the year in one problem there, right? I would say the most common mistake I see you guys making is forgetting that a square root can be positive or negative. You can't forget that. Very important. Another mistake I've seen us make throughout the year is breaking up a group too early. This q plus 3 group can't be broken up until we take care of this square that's tying that group together. Once we get rid of that square, it's no longer really a group. It's now just a q and a 3, and we can subtract the 3. But when they're squared, they're kind of bonded together there. You can't undo that. Sorry, you can't break them up. You can undo it with the square root. So you have to undo that before you can move that 3 to the other side. So number 9 I picked on purpose because I saw that it kind of has both of those things that have been giving us trouble throughout the year there in one problem for us to have a good, practice on here. All right. Let me see, what was the next problem I wanted to look at here? Number 15. Next one I have circled. Again, number 15 is still doing what we're calling the square root property here. So number 15 is 15. That equals 4 plus 3w squared. So here, it's nothing too special going on. I just wanted to again reinforce that we've got to isolate our quadratic, right? In this case, the only thing with w in it is w squared. So once we get everything except the squared part to one side, then we can take the square root. So if we took the square root now, right, we'd have square root of 15 on one side and square root of 4 plus 3w squared on the other side. That's not going to help us any, right? That square root hasn't helped us. So we can't just throw a square root at a quadratic. We've got to get everything except the square on one side first. Then we can use a square root and it might help us out. So first thing we got to do is move the 4 to the other side. So subtract 4, giving us 11 equals 3w squared. Wow, I'm sorry. I'm having trouble drawing 2's today. 3w squared. There we go. And now the only thing that's not squared on over here is that 3. So we've got a 3 multiplied here. So we have to undo that by dividing by 3. So we're going to divide both sides by 3. And that'll give us 11 over 3 over here on the left. And w squared over here on the right. Now that we have both of those things, we can take the square root. So now that our square root is all by itself on one side, not square root, I'm sorry. I'm so used to saying square root from chapter 10. Now that our square is on one side all by itself, right? W squared is all by itself. Now we can take the square root to undo the square. So that's what this is showing here, is you got to get your square kind of all by itself, then you can take the square root to undo it. So square root of 11 over 3 equals w, and remember that this can be positive or negative. I don't like that 3. That's a little better. Whatever. I'm not going to get too OCD about it. We're moving on. So another reminder, it's fine to have a square root of a fraction. Nothing wrong with that, right? You just take the square root of the top and the bottom. So, you know, it doesn't have to be pretty. Square root of 11 thirds is not, you know, a very easy to use number, but not all numbers are. So that's a perfectly acceptable answer. So let's move on to the next group of problems here, starting with number 21. And it's using something called completing the square. So before we jump into an example, let's kind of talk about what completing the square is. It's a trick, and I don't really like tricks. I don't know if you guys have noticed that about me. I'm more of a let's just do the math straightforward type of person. And so some of the tricks, like factoring by grouping from earlier on in the year, those aren't my preferred approach to problems, because sometimes the trick doesn't work. So I prefer to use other strategies. So I'm just going to say that very blatantly. I'm not a fan of completing the square. Yes, I do remember how to do it, and I'll show it to you guys how to do it, because I know some people really like the math tricks, and that's totally fine. Nothing wrong with that. I just don't like the math tricks. Not my style. So anyway, completing the square is a way of tricking a quadratic into being what we call a perfect square, which then becomes very easy to factor and solve. So what I mean by that is we have some sort of quadratic, right, where we have, you know, x squared. So before I start taking notes, why don't we have a label here? This is completing the square. So we have a quadratic where we have, you know, x squared plus some sort of something times x. And so what we want to do is we want to kind of trick it into being a perfect square. So, and let's go ahead and say this equals 0. So what we then do is x squared plus bx plus b over 2 equals b over 2, right? So if it's an equation, if we do something to one side, we're allowed to do it to the other side there. So we just added a b divided by 2, a 1/2 b, to both sides there. And when we do that, here's what happens. Now when we factor, we get x plus b over 2 squared, right? Because let's look at it this way. Hang on, I made a slight error there. Like I said, I'm not the biggest fan of the math tricks. B squared. No, I remember. You have to square this here. Sorry about that. See, like I said, the math tricks aren't my favorite part. Aren't my preferred approach to solving these problems. I usually just like to use the formulas. But anyway, so it's a way of making it so that you can factor it very easily. I totally botched those notes. Why don't we look at an example? I think an example is going to be a much better way to explain this completing the square technique. So number 21 says x squared minus 6x, and we need to complete the square. And it gave us, in red font here, a plus n, right? Because it's saying, what do we need to add to this in order to complete the square? So, in this case, our b, quote unquote, right, b is 6. So we need to have a b divided by 2 and then squared to add to it. So what that means is we need to take whatever is multiplied by x here, our single x term, which in this case is 6, and we need to, cut it in half and square it. And that's what's going to what we call complete the square. So we have x squared minus 6x plus 9, right? Because 6 divided by 2 is 3, and 3 squared is 9. And now when we factor it, we get x plus 3 squared. So that's why completing the square is helpful. It makes it super easy to factor. Just boom, done, factored, pretty straightforward. It's just not how I particularly like to approach these problems, because that's one of the great things about algebra. There's often a number of ways to approach a problem, and completing the square is just not the way I choose to do it. I probably haven't done completing the square since I was in Algebra 2, to be perfectly honest. But some people really like completing the square, and that's how they choose to solve these problems. So it's good to have a variety of approaches, and completing the square is one possible approach. So again, the goal is you take what is multiplied by the single x here. So we've got x squared plus or minus, doesn't matter, something times x. So you take whatever that something times x is and cut it in half and square it. And when that gets added on to the end there, you get, I'm sorry, I made a mistake. You get a perfect square. You just have to make sure you do the correct perfect square, right? So we need to make sure we get a minus 6. So it would be x minus 3 squared, not plus 3, my bad. So again, you take the center term there, what's multiplied by x, cut it in half and square it. I did a horrible job there on that example. Like I said, completing the square is just not my thing. If I had a little more time, I'd probably go back and redo this video, but you're getting the raw, unedited version here because I've been up a little too late, and I just don't have time to go back and do it better. So sorry about that. Let's look at 27. Another good example, and we'll make sure that I do it well enough that I feel okay about it. So y squared plus 5y, and we need to complete the square. So y squared plus 5y, 5 divided by 2 is, well, just a fraction, 5 divided by 2. So, bleh, fractions, right? So we can take y squared plus 5, oh my gosh, come on, plus 5y plus 5 over 2 squared, right? So we take what's in the middle, we cut it in half, and we square it. And that will help us complete the square. So now we can take y plus 5 over 2 squared, and we know it'll work out, right? Because our first terms will be y, right? Y squared. Our inner and outer terms will both be 5 halves y, so we'll have 5 halves y plus 5 halves y for a total of 5y. And our last terms will be 5 halves times another 5 halves, right? So what am I talking about here? I'm talking about FOILing. So y plus 5 over 2 squared is the same thing as saying y plus 5 over 2 times y plus 5 over 2. So when we FOIL that, we get y times y times 5 over 2, y times 5 over 2, and 5 over 2 times 5 over 2. So y squared plus 5 over 2y plus 5 over 2y plus 5 over 2 squared, which equals y squared plus 5y plus 5 over 2 squared. So I just did completing the square, but backwards, just to kind of show you why we do completing the square and why it works. It works because it follows this FOIL pattern, right? So you're kind of tricking the trinomial into being a perfect square, which then is very easy to factor. So instead of having this big ugly trinomial here with 3 different terms and fractions and all this ugliness, we can kind of shrink it down to this binomial here with just 2 terms squared. So now the kind of logical question is, why would we want to do that? Like, okay, yeah, we see why it works, but, you know, why? What's the point of completing the square? Well, you can use completing the square to solve equations that are quadratic. So number 35 through 51 are where you practice that, or maybe it was 53 in this assignment. I can't really remember, but whatever. The last part of the assignment is where we practice that. So we're putting these two concepts together. We're putting the square root concept together and completing the square. So 35 says that t squared plus 8t plus 15 equals 0. So normally we would say, let's factor that, and we totally could factor that, right? It would be very easy to factor 3 and 5. Obviously, 3 times 5 is 15. 3 plus 5 is 8. Boom, done. So this is not one where I would use completing the square, but the book told us to use completing the square. So that's what we're going to do to appease the almighty math book. So we take our middle term, right, 8, cut it in half and square it. So t squared plus 8t plus 4 squared, right? Cut it in half and square it. that's what we need to do. We need 16 there. Now, we already had 15. So I'm going to take a step back there. I'm sorry. I'm going to take a step back. Let's go ahead and make this what we just did there Step 3, I'm going to do something first that's going to make our life a lot easier. I'm going to move the 15 to the other side. So now we don't have to worry about the 15 for a minute because it's on the other side, right? So this is equal to negative 15, but we've added a 4 squared to the left side, so we're gonna need to add a 4 squared to the right side, right? You can't just willy-nilly add a 4 squared in there. It's an equation. Equation means that both sides are equal. So if we're going to add a 4 squared to the left, we add a 4 squared to the right. So what does that give us? It gives us t squared plus 8t plus 16 equals negative 15 plus 16. Sorry, I don't know where this random line came from. Now. And now over here we have t plus 4 squared equals 1, right? Negative 15 plus 16 is 1. So all of a sudden, through all of that seemingly nonsense math of randomly adding a 4 squared to both sides, we're like, why the heck did we do that? And now all of a sudden we have a nice little quadratic here that we can solve with a square root. So it's a math trick, right? We've tricked the equation into being a perfect square that we can now undo with a square root. So that's where completing the square becomes actually useful. Now, is that easier than factoring? In my opinion, no. That's why I prefer factoring. That's how I like to do these problems. Or if factoring doesn't work, I just straight up use something called the quadratic formula, which we'll be learning later on in chapter 11. So sneak preview there. But if you like these little math tricks, if that's the type of thing you like about math, then great, go for it. It definitely works. It's just not how I like to do it. So we had this random 15 hanging off the edge here. So the first thing we did is just kind of moved it to the other side so that we didn't have to worry about it for a second. And then we did our completing the square. We took our middle term, the 1 times the regular t, or up here it was regular x, whatever our variable is, and we cut it in half and square it. So we had an 8, half of 8 is 4, and square it. And we added it onto the end there. But we can't just add it onto the end of the left side. We had to add it onto the end of the right side as well. Because if you have an equation, if you do something to one side, you have to do it to the other side. You've got to do it to both sides. So now we've got to the point where we just have t plus 4 squared equals 1. So now we use the square root property, right? Square root to undo that. And square root and squared cancel, giving us a regular t plus 4 over here. And we have a positive or negative 1 over here. We don't know. Could be either way. So we got to do both. And that gives us that t equals negative 4, right? Because we had to undo the plus 4 with a minus 4. And we still don't know if that 1 is positive or negative. So t could be negative 3 if 1 is positive. Could be negative 5 if 1 is negative. We don't have any idea. Could be either way. So that's where completing the square becomes useful, is solving for quadratic equations. When you've got some sort of quadratic trinomial, as we do here, and we need to solve it. Completing the square is a way that we can trick the equation into falling into this square root trap, where we can then use the square root to undo the quadratic and solve for t, or solve for x, or whatever it might be. So let's do a couple more to practice just to make sure you've got it. Of course, this is an asynchronous day, so if you feel like you've got this already, you can turn me off at any time. But if you're interested, I'm going to do 41 and 49 here as some extra examples to help you out. So 41, negative 3y minus 10 equals negative y squared. Well, that's annoying. Let's get all of our y's on one side. So negative 10 equals negative y squared plus 3y. So I just moved the 3y on over to the other side there. But I don't like when my squared term is negative. It sometimes can make things a little more complex. Not always, but sometimes. So just in case, I like when my squared term is positive. So I'm going to negative everything. I'm going to multiply both sides by negative 1. So positive 10 equals positive y squared minus 3y. And now my y squared is positive, and I'm a little happier about that. So now we can complete the square, right? Cut it in half and square it. So we get y squared minus 3y plus 3 divided by 2 squared, right? Cut it in half and square it. And if we do it to one side, we got it to the other. So 3 divided by 2 squared also gets added to the left. Let's maybe see if we can do this in a way where we can tell what all the numbers are. Whatever. Haha, there we go. So 10 plus 9 divided by 4. So when you have a fraction squared, you just square both halves of it. So 3 squared is 9, 2 squared is 4, 9 divided by 4. And over here we've got y minus 3 halves squared. Right? Again, completing the square gives us that pattern where it goes from a trinomial down to a binomial. So this would be 49 over 4, right? Because 10 is 40 divided by 4. So add 9 more to that, and we get 49 over 4. So 49 over 4 equals y minus 3 halves squared. And now we can use our square root property and undo a square with a square root, keeping in mind the plus or minus situation that we're very familiar with now. So the square root of 49 is 7. Square root of 4 is 2. Could be plus, could be minus. And over here we have regular y minus 3 halves, because the square and the square root cancel out. So we add 3 halves to both sides. And we've solved for y, right? So the two possibilities of y are 3 halves plus 7 halves, which is 10 halves, or 3 halves minus 7 halves. 3 minus 7 is negative 4. Or a better way of putting that is y equals 5, 10 divided by 2, or y equals negative 2, right? Negative 4 divided by 2. And there we go. So again, completing the square, first we got to get it all set up properly. Then once we've got it set up, we divide by 2, or we cut it in half and square it. Yep. And we make sure we add it to both sides, right? So this side also gets a 3 halves squared, because we can't just do it to one side. That would be cheating. Got to do it to both sides. And then, because of completing the square, we get a nice, easy to factor squared term here that we can then undo with a square root. So a lot going on, pretty tough. Quadratics are very challenging. I'm not going to lie. Quadratics, I really wish I had given us a little more time. I thought we had one more week. I don't know why I thought that. Otherwise, I definitely would have cut chapter 9 shorter, so I apologize for that. That was error on my part. But we're going to do okay. We're going to get through this. And in the meantime, let's look at number 49. Number 49 doesn't look like a quadratic because it's 2w plus 5 times w minus 1 equals 2. So you're looking at that and you're like, there is not a squared anywhere. So what the heck? That's not a quadratic, right? Well, foil, right? We got foiled, to make a terrible pun. So when we FOIL this, we get 2w squared, and there's our quadratic. Our outer would be negative 2w, inner is positive 5w, and last is negative 5. So simplifying down, we get 2w squared plus 3w equals 7. So I added the 5 to the other side. And I combined the negative 2 and the 5 to get positive 3. So now we can complete the square. So the reason I wanted to show you number 49 was to show you that sometimes quadratics are hiding, right? If you're just quickly looking for a 2 up here in the power region, you're not going to find it sometimes. But when we did our FOIL, we realized, oh, there's our quadratic. We've got a 2w squared. So this is no good. Our completing the square trick doesn't know what to do with this 2 here. That 2 is going to confuse it, right? The cut it in half and squared trick only works on the middle number, in this case 3. We can't have a 2 there, so let's get rid of it. Let's divide everything by 2. Let's make that 2 just go away. And we can do that, right? It's algebra. We have that power. As long as we do it to both sides, we can pretty much do whatever we want. So let's divide the whole thing by 2 to make that 2 go away. So now we have a regular w squared. We've got a 3 divided by 2, w. And we've got a 7 divided by 2 over there on the right. Now we can complete the square because we've got a 1 over here in front of the w squared, right? So w squared plus 3 halves w plus cut it in half. So now it's 3/4 and square it. And that equals 7 halves plus 3/4 squared. So over here we know how the pattern works by now. We've got w plus 3/4 squared, right? Whatever the cut in half thing is, that's what goes in here. I think we've caught on to that pattern by now, right? Because up here we had 3 divided by 2 squared and 3 divided by 2. And in this case it was negative because the 3 was negative. Up here we had 4 squared, and when it was all said and done, we had t plus 4, right? So whatever ends up being squared, that's what ends up in our completed square there. And over here, this is going to get a little messier. So 3 squared is 9, 4 squared is, oops, sorry about that, 4 squared is 16, and well, that's kind of an ugly fraction, isn't it? So w plus 3/4 squared equals 16 times 8, so 7 times 8 is 56 sixteenths plus 9 sixteenths. So we get w plus 3/4 squared equals 65 over 16. All right, did I do that right? no, that checks out. So that math all looks good. Yeah. It's just a really ugly fraction. Like I said, sometimes the answers aren't pretty. So now we need to take the square root of both sides, right? So w plus 3/4 equals the square root of 65 over 4. That can't be right because 65 is not a square. Hang on. Gotta think for a second. Did I do this correctly? Yeah, no, that's exactly what they say to do in the example problem. So it might just be one of those cases where you get a really, really ugly number as an answer, right? Because 7 times 8 is 56. That's all right. Yeah, there's no doubt about it. So it's just a really ugly answer. So that's okay. Square root of 65 is not 65. 5 times 13. Yeah, you can't simplify that at all. So that's not getting any more simplified than that. Because square root of 65, when we factor 65, we get 5 times 13. So those are both prime. So you can't simplify the square root of 65 at all. So that's as simple as it gets. So we get w equals negative 3/4 plus or minus square root of 65 divided by 4. And that's as simplified as we can get, because the square root of 65 doesn't simplify any. So sometimes math is ugly, and this is about as ugly as it gets, with a square root and a fraction and another fraction. So if you find that I have made a mistake in number 49, which I think is kind of likely because usually the math book doesn't give you such an ugly answer, then please let me know, and I would be very happy to see where I might have gone wrong somewhere. It's definitely possible. Let me check. Yeah, that's positive 3w. Copied the problem down wrong, which has been known to happen. So let me check the original problem. Well, all right. So as far as I can tell, it's just an ugly answer. But please let me know if you discover something differently as you're working. So have a great day. I will see everyone tomorrow at 9 o'clock for our regularly scheduled class.